All right, should I start? Yeah. Okay. So, hello. Good afternoon. My name's Adam Smith. I'm a faculty member in computer science here. Okay, well, the title of my talk is Accuracy Isn't Enough, Privacy and Fairness in Machine Learning. And I'll be talking about two projects that I work on, one very recent, one that spanned the last decade, and how they relate to AI. So I wouldn't describe myself as an AI researcher normally, although I do publish in relevant venues. I come to this from a perspective, my background is in cryptography and sort of computer security and data privacy. And so the kinds of questions I ask are probably quite different from some of the things that were discussed earlier, although maybe there's some overlap. Okay, so of course, data-driven systems broadly are guiding decisions in many areas of our lives, and this is increasingly true. We're sort of figuring out ways to automate decisions about all sorts of things that previously required extensive human judgment. And I'm thinking of things, everything from predictive policing, various kinds of precision medicine, decisions about, say, bail, whether or not somebody should be let out on bail, are now informed by scores that are produced by an automated system. Credit decisions, of course, have been partially automated in this way for many, many years, where credit scores are the kind of guiding, the main signal that lenders might use to decide whether or not to offer somebody credit. For good reason, the vast majority of research in this area seeks to make these systems, more accurate, perform better in terms of computational efficiency, in terms of various measures of performance. But I'd like to kind of lead us to a different set of questions. Maybe that came. I'm not sure. I unfortunately missed the panel, so I would imagine some of these came up at the panel. I'm not sure. So on one hand, it seems we are often in situations where we're trying to balance conflicting goals. On one hand, we're trying to get the benefits of using these vast amounts of data we now have and collect. On the other hand, we have considerations that don't neatly fall into sort of measures of accuracy or false positive rates or things like that. Considerations like privacy, like what is revealed by the output of some system that is about the data that were used to train it. Transparency, this definitely came up earlier. Questions of control, like who decides how these systems work, and is that the same people who used to decide? And actually, one of the things that we tell our students a lot now in computer science is that they are going to be in positions where they are going to be designing systems that make really important decisions in a way that maybe other fields of engineering have wrestled with for years. Think nuclear engineering or things like that. But that for computer science, for software, is somewhat more recent. So I'm interested in understanding how these different considerations trade off against each other, and how we can understand exactly what these other goals are, because they're much harder to measure generally than straightforward things like false positive rates. A bit more specifically, I come from a theoretical background, so the angle that I'm most interested in is trying to understand specific aspects of these questions that we can formalize mathematically. And there are a number of reasons for this. One is that when we can pin down very precisely what it is we're trying to accomplish in a particular situation, allows us to eliminate ambiguity. It allows us to more explicitly specify, what it is we're trying to accomplish exactly. What do we mean by a term? For example, in the context of data privacy, is there an attacker? What are her goals? what resources does she have, and so but when we pin these things down precisely, it makes it much easier to discuss them and consider, compare different notions and things like that. Potentially, it gives us, the ability to automate decisions about these sort of meta decisions, like are we providing a sufficient level of privacy in a particular application, or are questions about, are errors fairly distributed across different groups of people, and I'll talk about that a little bit afterwards. Again, of course, this is important. This type of automation is important if you want to be able to make these types of decisions at scale. And maybe one of the things I don't have on the slide, but another important aspect of trying to nail down these sort of English language notions like fairness or privacy mathematically is it allows us to make very precise claims about a system, and those claims can actually be refutable, which is really important. So as these questions become more important, we need to be able to sort of discuss these things scientifically. And so my interest, as I said, is in trying to kind of nail these ideas down precisely and reason about them. Of course, the downsides of sort of mathematical formulations is sometimes they can be hard to understand for a broad audience, and that's really important for these aspects that really touch on, that are really about like where does these decisions take society. It's important that we be able to discuss, well, as a society, what we're trying to accomplish, and as these things become more technical, that becomes harder, and that's unfortunately, I think, unavoidable. And maybe another point is that these very rigorous formulations may be less flexible than a kind of a natural language description, in the sense that you might have to come up with new formulations as the setting changes. But again, I'm not sure that's avoidable. Okay, so that's just my a broad description of what I'm interested in, what I'm after, and I'll talk about two versions of this. One is related to privacy and statistical databases. That's something I've worked on for the last 15 years, and it's probably the bulk of my research from those years. And then a more recent project on distribution of errors and fairness, and I'll describe what I mean by that when I get there. Okay, so consider the following setting where I'll first talk about privacy and statistical databases. Consider an organization, and a good example to have in mind is the Census Bureau, that collects information from individuals and wants to make that information as available as possible for statistical analysis, possibly by publishing a bunch of tables, possibly by answering queries from researchers. There's nothing really specific about the census. This type of problem comes up, this general setting comes up in lots of applications. Public health data, social networks, data from social networks like, Facebook's, for example, collects information and tries to make information about what they call audiences available to advertisers, for example. And in all these applications, there's a real benefit from having this data and analyzing it and using it to make decisions. But on the other hand, these are generally fairly sensitive data sets. And so we want to understand how we can get their benefits without just sort of publishing people's data, on the web, without just while providing meaningful guarantees to individuals about their privacy. Okay, and so that's, as I said earlier, my research is really oriented towards trying to find rigorous foundations for this area and provide mathematically clear guarantees about the systems we design. There we go. Okay, so we've got this sort of general problem. We want to publish it. We've got some data set. We want to make it available for analysis. The first thing we might do is just sort of do the obvious thing, which is to look at the data and decide which fields could identify people, things like names and social security numbers and telephone numbers, and just strip those out of the data and publish whatever's left. Okay, just share that data. Okay, and the problem, there are a number of problems with this. One is that sometimes the thing you want to study about the data could could have to do with what was these identifiers that were removed. For example, if you're looking at the spread of a disease, you might need to know exactly where people live, not just what city they're in, but like some very specific information about what they live. But maybe the more fundamental problem is that it doesn't work. So consider the following sort of toy example. Here's a photograph of somebody whose face has been helpfully grayed out. So most of us can figure out who that person is, not because we can see their face through the gray blurb, but because there are all these other cues in the picture that we kind of can connect to what we know about the world to know that there aren't really that many people who stand in front of that kind of podium. Only one of them in the last 200x years has had brown skin. We know exactly who that is. And this is obviously a toy example, but actually there are sort of lots of published examples where these sort of naive attempts at anonymizing data have failed miserably. For this particular example, people looked at the typical blurred faces on videos thing that you might see on TV or on YouTube. You can just train an image classifier to classify blurred faces, and it'll work just fine. In another example, people have showed how you can recover lots of information about a person from their genome. I'll skip over these examples quickly. There's another fun example that you can read on the web about how about a taxi data set in New York City and how individual riders were re-identified. This sort of common thing that these kind of failures of attempted anonymization have in common is that they try to separate variables into things that identify people and things that don't. And the problem is that information about people, almost every type of information, if it's present in more than one place, can be used as some sort of identifier. And we have to reason about attackers that have other sources of information, not necessarily only the ones we know about, but the ones that we may not know about or that may arise in the future. And because of these problems, anonymization schemes, or straightforward anonymization schemes, are regularly broken. You might think that maybe the problem is that we are only releasing that in these examples we're releasing very individualized information. We're trying to publish a data set where we've kept the record structure, so we still have one record for each person, but we've somehow transformed each record. And that maybe the solution is just to publish aggregate information, maybe just counts of how many people have a particular set of properties, how many people live in Boston and are graduate students in computer science or things like that. But even that's problematic, and that's because if you take a lot of these aggregate statistics together, they can effectively encode the data set. And there are a number of ways this has shown up in the literature, and these are citations to my own work, but there's sort of lots of work by other people here also. Just to take a really simple example to make it concrete, imagine I publish the average salary in this room immediately before and after somebody walks out of the room, right? So I know how many people are in the room. If I know the average salary, either of those averages taken individually doesn't seem to tell me much, but if I know the difference of those two averages, then I know exactly how much, what that person's salary was. And so that's a really simple example, but these things happen in much more subtle ways at large scale. When you're publishing lots and lots of information, it's often possible to reconstruct the data from these many statistics. Okay, and so the brief lesson of these results, sort of summarizing very at a very high level here, is that we can't release everything everyone would ever want to know, and we need to kind of reason more precisely about what's going on. We need tools to reason more precisely about what's going on, and that's sort of what I'm interested in. As I said, I'm interested in rigorous formulations. I'm interested in algorithm design, various kinds of attacks on these systems, and sort of connections to other areas. So one notion that's come out of my work that has been fairly influential is called differential privacy. It's deployed in a number of current systems. So if Apple uses systems that satisfy this criterion to collect information about how people use iOS devices. Google's Chrome browser uses this to collect information about browser settings. The US Census Bureau is aiming for the public data products from the 2020 census to be to satisfy the type of guarantee I'll explain. And it's led to a big field of research that touches many areas, in particular statistics and machine learning. The basic idea is the following. It's a thought experiment. I'll try and formulate a condition. I want to formulate a condition on this algorithm A that processes a data set and produces some output. And I want to formulate a condition that sort of is meaningful, gives me a meaningful guarantee about what can be learned about any individual in this data set. And the way I'll do this is I'll compare two different worlds, one in which I've got the real data set, and a hypothetical world in which some person's data, maybe my data, have been changed. And the question we'll ask is, will the probabilities of different outcomes in these two worlds change? Will they be similar between the two worlds? The requirement on the algorithm will be that they are similar. And so pictorially, imagine that I've got a red distribution and a blue distribution and a green distribution, so they correspond to the kind of real and hypothetical worlds respectively. And what I'll require is that for any any set of possible outcomes, in this case, I'm imagining the outcome being a single real number, but it need not be. What I'll ask is that any set of outcomes should have about the same probability in both worlds. And the result of that is that, for example, I can ask, well, what's the chance that I'll be denied health insurance based on the fact that this clinical study was published? Well, that chance is about the same whether or not my data were actually in the clinical study. Okay. So it gives me a fairly strong guarantee. So it implies something like this. No matter what an attacker knows ahead of time, they learn about the same things. They learn almost the same things about me, whether or not my data are used. I'm sorry, I'm not speaking into the microphone. I hope that is okay. And so one of the things I'm interested in is designing, and I've spent a lot of time on, is designing algorithms that satisfy this kind of criterion. And do useful things. So, for example, I work with the Census Bureau on developing methodology for publishing, useful information that they collect based on what they collect. I've worked on algorithms for various machine learning and statistical inference tasks, and I'm happy to tell you details offline. So, in the couple of minutes I have left, I'm gonna talk about another facet of this that I'm interested of these broad questions that I'm interested in. It has to do with fairness. Fairness is possibly even more of an overloaded term than privacy. It means like many different things in many different settings. It's sort of often used as an umbrella term for a kind of a set of properties that people, especially in machine learning, and have been trying to understand more in the recent years. Maybe the 4 or 5 last years have seen a surge of activity in this regard. So to make it concrete, imagine a classifier used to predict a binary feature, and I'll pick sort of a toy example. Imagine I'm looking at grad school applications in computer science. So the input is the text of the application. The desired output is some a correct prediction of this person's future, right? We all know there are 2 possible outcomes in computer science grad school. You either leave with a PhD, or you don't, and you go to industry and make twice as much as your advisor ever did. So that's the failure mode. And so consider an admission process that historically has discriminated against some group of people, and again, to keep it light, let's say we discriminate against people who don't really like science fiction. Okay, so we've got two groups. The sci-fi lovers, that's the vast majority of our applicants, and then everybody else. And so the question we might ask is, how are, does our classifier, of course, won't correctly predict every time. The only way to correctly predict is to put somebody through grad school and see what happens. And so what we can ask is if the mistakes that the classifier makes are sort of evenly distributed across groups in some sense. Okay, it's hard to nail. There are many ways to nail that down, but hold on to that for a second. And why might they not be evenly distributed? Well, our classifier was trained on data. It could be that there's just way less data about the people who don't like science fiction. Or it could be that our classifier is picked up on some weird feature, like if your grad school application talks about how Star Trek inspired you to go into technology, then maybe that's like a really good predictor for something that just isn't present in Group 2's applications, right? So again, this is a toy example, but I don't think it takes a lot of imagination to see how this comes up in real and very serious examples. Okay, so what we're interested, I'll just skip ahead. This is a project that started with Ron Canetti, who's here, and one of our students, Sarah Scheffler, and some collaborators at MIT. And we've looked at understanding how these different measures of fairness, of fair distribution of errors, behave when systems are put together into more complex systems. So in particular, we looked at the measures that have been proposed for soft classifiers that output a probability, and there's a notion called calibration, and sort of measures that were proposed for hard decisions, such as the final admit or decline decision you might make. And what we show is there's this sort of inconsistency between these approaches. So even if your soft classifier satisfies various nice properties, it could be that there's no way to use it to make a final decision that satisfies this sort of analogous properties for hard classifiers. So what we're trying to understand is sort of how do these measures of fairness really behave? Are they meaningful? In what kinds of situations? And that kind of thing. Okay, so I will stop there. I had couple of slides, but I'm already over time, and I'll just leave you with this slide. All right, thanks very much.